know when you have 5 minutes, and we'll take questions at the end. So please go ahead when you're ready.
Thank you. Thanks for the introduction. So let me talk on this topic, which is kind of become quite a hot topic these days. First, let me just briefly summarize what prime order black holes and what scales we're talking about and so on and so forth. I guess probably for most of you know all this, but just to remind you what I'm talking about, let me just show you this sort of a space-time or time-space diagram, cosmic space-time diagram. The horizontal axis is the number of E-folds, and the vertical axis is the logarithmic of the length scale. And in this diagram, of course, the sort of a constant co-moving scale will be just a straight line. And as we all know that during inflation, the Hubble radius is almost constant, and it ends with some kind of reheating. We don't really know what kind of mechanism it is, but we believe that after this reheating, our universe became hot radiation-dominated universe, and which lasted until quite recently, until maybe the redshift of about 10,000 or so. And then what we know now is that the dark matter dominates our universe, and eventually some dark energy seems to be dominating today. But since we're not talking about, I'm not talking about the future, I'm talking about sort of past. Forget about these dark energy components. And let's focus on what could have happened, let's say during inflation. We know essentially, oops, there must be something wrong with this figure. Sorry. Anyway, this is the famous constraints from CMB observations, and we know that all these CMB observations are related to those so-called cosmological scales, a very, very long distance scale, close to the co-moving scale of current Hubble scale. If you go back in time and then you hit the time when this current Hubble scale hits the horizon scale during inflation, the number of E-fold, approximately about 120 before, I mean, backwards in time. And for some reason, I mean, this is just some because of this radiation dominance and the inflation. But anyway, we think that the inflation has lasted about 50 to 60 E-fold. So in terms of number of E-fold, actually the inflation is half of the history of our universe if you consider the whole observable universe scale. Now, and in the current large-scale structure and CMB observations only tells us the very, very large scales, and we don't really know what would have happened this latter part of the inflation. So this would be the part we know would be only about 10 E-folds or so, and there should be another 40 to 50 E-folds of unknown physics. But these days, the people started to think about maybe there are some interesting physics going on, especially when there are some particular features in the power spectrum, which is not totally constrained by these large-scale observations. On small scales, maybe you have some interesting peak, and these peaks can lead to I mean, if the peak is large enough, then it can lead to a primordial black hole formation when the scale enters the Hubble horizon again during radiation dominance. So, and actually there are interesting scenarios and interesting maybe indications, suggestions already these days, which actually tells us this primordial black hole really may exist. So today today's my talk is that so if they actually exist, and what kind of information can we get, and also how do we detect them, and how do we use it for cosmology and so on and so forth. Oh, by the way, if you have any question, I don't know if there's any how to see it, but anyway, if you just scream or I don't know, say something, then I will stop talking and then try to answer your questions. Okay, so what we know from, by the way, so this sort of a primordial perturbations, the so-called primordial curvature perturbation, this is just a power spectra, and it is usually assumed that they are Gaussian, meaning that the distribution with this fluctuations will form some Gaussian form, with this width actually corresponds to this power spectrum, and if in the case of those power spectrum on a very large scale, since this is the like 10 to minus 10, or in square root of it 10 minus 5, so the width, the dispersion will be the 10 to minus 5. Well, if you want to have some primary black hole, you need to have some sharp peak, but this peak yet should not to be too large, because if this is of order 1, for example, then the whole universe would become black holes in the very early universe, and that would definitely contradict our observations. So this should be a highly peaked, but still not too large. It's smaller, and usually we think that this is approximately like 10 minus 1 to 10 minus 2. So anyway, so it's larger than this large scale CMB observed part, but still it's smaller than unity. And so this means that this width is much smaller than unity, while of course the primary black hole can only form on when the perturbation is very large and positive. So this the critical say threshold, for example, delta C would be of order 1, or here it's the it is sort of from various computations that usually it is assumed it's probably around 0.4 or so. But anyway, it's order 1. And as I said, this sigma m, this corresponds to the power spectrum, sigma square is a 10 minus 2 or so. So this is exponentially a very this exponent is very large with this minus, so it gives you a very small probability. But even if this gives a very small probability, since primary black hole, once they are formed, they behave like dust matter particle, while the radiation decays like 1/8 to the 4th. So eventually these matter components start to dominate the universe. So even if for very small beta, eventually if the primary black hole forms very early universe, then it can dominate our universe. And eventually you have some very strong constraint on this value of beta. Now, after sort of, I mean, evolving this, once you know this beta and then evolve this to by today, then it will be sort of a, as I said, it behaves like matter. So it may be it may constitute part of dark matter, cold dark matter of the universe, or maybe the whole cold dark matter. And there are lots of constraints on this. And this F is just a fraction of primary black hole in the dark matter. And there are many, essentially the gravitational lensing observations, which constrains a very large sort of area of the say mass scale of primary black hole. However, there are a couple of interesting regions. One region, which is this completely, in some sense, empty sort of regions where there's no really strong constraints, which is around the mass of 10 to 17 or 18 to 10 to 22 grams. If if primary black hole mass is in this range, actually they can be a cold dark matter of the universe. And so this is a very, very interesting possibility that I mean, it's may not be so interesting for particle physicists, but it's an interesting possibility that maybe the dark matter is not a some kind of elementary particle, but a primary black hole. Another area is, although it's probably much smaller than, say, a small fraction of cold dark matter, but it, in the region where the mass is of the, say, solar mass or 10 solar mass, maybe 100 solar mass, 10 to 100 solar mass, those masses are in the range of recent observations by LIGO-Virgo. These LIGO-Virgo gravitational wave detectors have detected lots of merger events, and many of them seems to be a binary black holes. And although there are some scenarios of astrophysical scenarios to explain such those binary black holes, there's still a quite a interesting sort of a, let's say, a possibility that they, even if not all, but many of those binary black hole are primordial. So that's these are two are essentially very interesting. There are many other sort of interesting sort of regions and also interesting sort of indications in these days, and possible detections. For example, by this Subaru HSC have it's not detection, but the observed one event which looks like a primordial black hole. Although since it is just a single event, it's very difficult to justify whether it is the case. So they are actually doing a further observations, and within a couple of years, probably we know whether there are some primordial black holes of this some planet sort of a size primordial black holes of this in this fraction. Okay. Anyway, so the most important or a sort of a fact which has realized in the last maybe 5-10 years is that of course, when you have some primary black hole formation, as I have said in the beginning of this talk, you need to have some fairly large curvature perturbation. So and but not all those fluctuations will form primary black hole, but only peaks, only large peaks of those large fluctuations peak primary black holes. While the other ones, which below this threshold, eventually when their scale enters the horizon during the radiation dominance, they start to oscillate. They start to oscillate like sound waves. And these oscillations, of course, is essentially a oscillation of space-time, and which means that you would produce some gravitational wave. So these are called induced gravitational wave or secondary gravitational waves due to the some primordial curvature perturbation. So if you have some scenario of generating some curvature perturbation, then which can lead to primary black hole, then this is sort of a automatic that you then have some associated induced gravitational waves. So there's a very, very strong sort of correlation between the existence of primary black hole with the existence of induced gravitational waves. And interestingly, if the primary black holes are cold dark matter, which is the this range, if this is in this range, and if then the frequency of gravitational wave will be about the 10 to minus 3 hertz, which is right in the middle of the Lisa band. So this is a something which is very interesting, some interesting sort of possibility for the future Lisa observations, hopefully within 10-15 years. Another thing, which is although the primary black holes are not a dominant component called dark matter, but still, as I said, they may be some part, at least some part of LIGO of black holes may be primordial. In this case, if you assume primordial black hole to be, I mean, 10 solar mass, that's exactly what those LIGO black holes are. Then frequency of those gravitational wave will be about 10 to minus 8 hertz. And actually, this is in the so-called pulsar timing array experiment band. So this is already ongoing, and actually, I will just tell you that these days we have some interesting results. So this is what you can do. I mean, this has it's interesting in this Saito and Yokoyama. Those people published this paper. I think this is very important seminar paper already like 12, 13 years ago. But anyway, and realizing these two important regions. The one is the region where the black hole is almost all the cold dark matter, and the mass in their case they assume 10 to 20 gram. It may be 21, 22. It doesn't really matter. But the point is that this region actually crosses with is above this LISA sensitivity. So and which is very well above LISA sensitivity. So so once LISA flies, and there's a very good chance that we see those background cosmological background gravitational waves due to these large curvature perturbations. But if we don't see it, actually it would constrain this primordial black hole scenario very severely. Another reason, which is of the current interest, maybe, is that if the primordial black hole is like 10, in their case, they assume 100 solar mass. But anyway, although the fraction of black holes is small, in their case, it's like 10 to minus 4 or so. Even in this case, signature of the gravitational wave spectrum peak would cross this pulsar timing array experiment. It's very close. And actually, probably many of you know that in just the a half year or maybe or almost a year ago, there was this announcement by a Nanograph, a collaboration, saying that maybe they have seen some induced gravitational waves, or at least they obtained some strong constraints. Now, if you then with this constraints in mind, so this is the current sort of a constraint at this 10 to 8, 10 to 9 hertz. Then assuming, for example, these people, that assuming that you have some peak of the mass spectrum of the primordial black hole around, say, 20 solar mass or so, then they say that if the distribution, probability distribution is Gaussian, then it should have been already seen in those pulsar timing experiments. And since we think it's those experiments are now giving some upper bound, then it sort of already constrain this model. Either this kills the model that those primordial black holes, the LIGO black holes are primordial, or their distribution function should be non-Gaussian. Anyway, I guess you have seen a lot of papers, the implication of this Nanograph results in the archive and so on. So there are some very interesting things to work on. Anyway, so far I have discussed the case of the initially curvature, the sort of primordial curvature perturbation, but there can be some isocurvature perturbation, especially on small scale. We don't have a very little constraints on the amplitude of isocurvature perturbation. So so that's another interesting thing, and especially one very interesting thing is the isocurvature perturbation due to say black holes, very small mass black holes, which have evaporated already in the very early universe. Now, if the black holes, due to the Hawking radiation, if mass of black holes less than, say, 10 to 8 gram, then they evaporate within about a second. So this is before the Big Bang nucleosynthesis time. And it seems at first glance, we cannot have any constraints on such models. But actually, we can, because if you think about such as, say, small primordial black holes, they form in the very early universe. So even if the number of those black holes are small, they can easily dominate our universe. So in the beginning, you have some primordial black hole forming, but their total density is much smaller than radiation density. But eventually, they become dominate the universe. But since the primordial black hole formation probably occurs randomly, just occurs, this is a rare event and which just occurs randomly at some peaks of the curvature perturbation. So you will have some inhomogeneous distribution of primordial black holes. And this inhomogeneous distribution of primordial black hole turns into adiabatic perturbations of space-time when those primordial black holes start to dominate our universe. Now, but these black holes, since their mass is small, they evaporate eventually, and the universe becomes radiation dominated again. Now, then this after the evaporation, of course, they start to oscillate, and they produce gravitational waves, as we have discussed. So you actually, although the primordial black hole itself may have just evaporated completely, and we don't see any trace today, you may see the effects through this induced gravitational waves. Now, so this we have discussed recently, and actually we obtained some interesting result. The point is that if the decay of a primordial black hole or evaporation primordial black hole is like decaying particles with some constant decay rate, then actually there won't be a sufficient interesting amount of gravitational wave produced. The reason is that the decay occurs within or over a couple of Hubble time, and so essentially, even if originally you have some other perturbations, but during radiation, matter dominance, this is essentially a kind of frozen. As you know, in the matter dominate the universe, the gravitational potential remains constant in time, at least in linear theory. So this is just a frozen pattern, so it doesn't produce anything. But when the universe becomes the radiation dominance, of course, they start oscillates and produce gravitational waves. But if this transition is very, very slow, then during this phase transition, this initially frozen fluctuation start to move, but they essentially decays out before you actually have some oscillation. It's like, for example, if you consider some, say, star or the sun or something, which it has some mass. This is a mass inhomogeneity, and if they all of a sudden evaporate or they explode and they become radiation, and then of course in the case of sun, it's sort of spherical symmetric, so you need some maybe two suns or something, some asymmetric matter. But anyway, when they evaporate instantaneously, then you can produce some large gravitational waves. But if they gradually decays out, then of course you can never produce any appreciable amount of gravitational wave. So this is the case of the decaying particles. But interestingly, in the case of primordial black hole, because the primordial black hole has some definite sort of evaporation time, if you consider the time scale of evaporation black hole, actually it becomes the time scale becomes shorter and shorter as the evaporation proceeds. And this is like the picture. So this blue line is the relative sort of a density of the primary black hole. So it starts to dominate the universe and becomes one, and then start to evaporate. And as soon as it starts to evaporate, radiation starts to dominate the universe quickly. And so in this sense, the evaporation primary black hole can lead to a fairly instantaneous transition of a matter-dominant universe to a radiation-dominant universe. And because of this, you may be able to produce huge sort of amount of induced gravitational wave. And if you assume, say, initial Poisson distribution of primary black holes, then it turns out you will have some k to the 5 power peak. So this is the characteristic sort of a peak, the spectrum and peak of this gravitational wave due to the transitions of universe from a primary black hole dominant universe to the radiation dominant universe due to the evaporation of a primary black hole. So this gives us interesting constraints. For example, you have some constraints on this beta. Of course, beta is this fraction of the primary black hole when they are formed, and this cannot be too large, because if this is too large, then they dominate the universe until quite late, and that would contradict with the nuclear census constraints and so on and so forth. While if it is too small, then you wouldn't have any of those black hole dominated stage. So the regions we can actually test is this range, which is not too large, but it's very, you have some nice, interesting stage where you can test this scenario. Now, in this scenario, then we have some sort of a dependence of mass and frequency of the gravitational waves, and also this, for example, some spectrum for a given certain model. So, of course, it does depends very much on what kind of parameters you assume, but there are some interesting possibility. For example, even by advanced LIGO may be able to see this peak of k to the 5 power peak due to this already evaporated black holes. There are some caveat in this discussion. The very important discussion the issue is that actually what we have discussed so far relied on the linear theory of cosmological perturbations, but actually most important or interesting sort of part is nonlinear. You could actually see already from this expression that this is the initial isocurvature perturbation, and in initial isocurvature perturbation is it's the close to one. It's the so this is like 1/6 or something. So amplitude is smaller than 1, but not too small. So at the peak already. And if you follow the observation, the evolution of these perturbations, you find actually there are some finite range of a sort of a frequency of the wave number, where actually the density perturbation has already become nonlinear. So this means, although the metric perturbation is already small, apart from this the UV cutoff scale, most of the scales, the curvature perturbation is much smaller than unity, but since the density perturbation is larger than unity, the evolution would be nonlinear. So you actually have to consider some nonlinear evolution. Anyway, so there are some interesting sort of issues remained, but at the same time, what I want to say is that there are some very interesting sort of cases due to this isocurvature perturbation. So far, most of the work in the literature is about the curvature perturbation, primordial curvature perturbation. But if you once include some possibility of primordial isocurvature perturbation, there seems to be a lot more interesting scenario possible. Anyway, so this is the take-home message. First of all, primordial black hole may play central roles in gravitational wave cosmology. As I said, especially in the cosmology, in the case of cosmological gravitational background, primordial black holes are crucial sort of ingredient of those physics. Now, and this recent and more, not more, I should say, I shouldn't say more, but the recent additional interesting frontier of this this area is this case of isocurvature perturbation, and especially nonlinear isocurvature perturbation. They may play very important roles in primordial black hole gravitational wave cosmology. Okay, thank you very much. So maybe I should have stopped somewhere, but anyway.
No, you're actually 3 minutes ahead of schedule, so thank you very much.
Okay, great.
That's excellent. We had a hand raised from Subodh before, Anish. So Subodh, if you can unmute yourself and ask your question or make your comment, please.
Sure. Hi, Michelle. I was very curious about you're saying that black hole evaporation, if it proceeded fast enough, could produce gravitational waves, but not if it proceeded slow enough. Did I understand that correctly?
Yeah, so if the black hole gravitational wave, evaporation goes very slow. I mean, well, that's actually the case when you have a very wide, say, mass spectrum. Yes, if the mass spectrum primordial black holes are large, the width is large, like more than say one order of magnitude, let's say. Then the evaporation time would have some width, and this width would give rise to very, very smooth transition of matter dominant universe to the radiation dominant universe. And in this case, you do still produce some gravitational waves, but the amplitude wouldn't be so large.
Okay, so I just want to make sure I'm understanding. So it's these gravitational waves are being produced by the particles emitted via Hawking radiation. Is that correct? Or no?
Oh, no, it's not by particle. It's the distribution of the black hole itself. So you see that the primordial black hole are not uniformly say created, so they will have some inhomogeneous distribution, and this inhomogeneous distribution of primordial black hole produces inhomogeneity in the the density of the primordial black.
Okay.
It's sort of a smeared density, huh? I mean, you have to smear out. This is so primordial black holes are like particles itself. Okay.
Yeah. No, thank you. That clarifies it. Thank you.
Okay. Thank you.
Anish, do you want to go ahead?
Yeah. Yes, so I had a couple of questions. One is that, so in one of the scenarios, you showed that the first order scalar perturbation via mixing is sourcing the second order tensor perturbations, which we see as gravitational waves, right?
So I cannot hear you very clearly. Maybe
Hello? Something
wrong with your microphone. Sorry.
Can you hear me?
Yeah. Can you maybe speak louder? Because Anish? Oops. No.
You need to unmute yourself.
Yeah. Can you hear me now?
Yeah. But anyway, try to speak louder, please.
Yeah. So my question is that, so in one of the scenarios, you are using first order scalar perturbations to induce second order tensor perturbations, right? So so my question is that, do you also imagine a scenario where you can also induce second order vector perturbations as well, and then maybe generate some magnetic fields or something like that from the mixing of first order scalar perturbation? or do they always decay?
That you know, maybe yes. I have not considered such cases yet, but if you have some interesting sort of coupling, yeah, well, actually, at least you have some gravitational coupling. But if you have some, interesting coupling between some vector and this scalar, yeah, so it should be gravitational, huh? Some gravitational coupling. Then, yeah, you may be able to produce some interesting vector perturbations. Yes.
I see. And
Yeah.
and the second point I wanted to ask is, could you comment on how much accretion we might expect after the primordial black holes are formed and then evolving later?
Oh, yes. That's a very interesting, good question. Usually, during the radiation dominance, accretion won't affect much. I mean, you can sort of easily estimate how much you can gain from, say, some radiation, surrounding radiation. And so in the radiation dominant universe, at most, the mass of the primordial black might say increase by a factor of maybe 50%. That's at most. That's all. Maybe factor 2. Anyway, it's much less than factor 2. But after the universe becomes, say, matter dominated, dark matter dominated, then it all depends on how this sort of a nature of cold dark matter is, and so on and so forth. As you might form a very interesting, say, accretion disk around. It depends on the primordial black hole mass as well, around the primordial black hole in the very, very early universe, like redshift of maybe even 100. Huh? Then you may have some very, very interesting effects. So in this case, you might have some very interesting accretion effects, and that's another interesting areas. But as far as I know, those would be important for fairly large mass black holes. Yes. Yeah, I mean, like maybe more than at least 100, 1,000, maybe 10,000. Maybe I'm wrong, but that's my impression. Yes. So for small mass, let's say mass less than 1 solar mass, the accretion effect probably is much less.
Thank you.
Before we move on, we've got a question from Vahid, who says, let's forget about gravitational wave detections. Is there any other way to detect the PBHs astronomically? Do you have any ideas?
Yeah, so there are actually, where is it? Yeah, so in these sort of regions, very large mass regions, we do have these gravitational lensing observations, which can constrain all these the amount of primordial black holes. Even in this range, there are some suggestions that to use, for example, very, very low frequency, say radio waves and so on. Sorry, the other way, high frequency gamma rays and so on, to see kind of gamma ray gravitational lensing, huh? to constrain these regions. I don't really know about all these things at the, but there are several ideas, but not really definite yet, and we don't really know whether it works. But yeah, so in that sense, if actually we have some primordial black hole in this range, one of the I wouldn't say only, but sort of the most important possibilities to detect gravitational waves. But by the way, so there are some, for example, some discussions about the effect of those small primordial black holes captured by neutron stars. And if neutron star capture those black holes, then eventually it might sort of implode and explode and so on. So such an event may be visible. I mean, in some optical observations or any electromagnetic observations, and so so that's another thing. But I don't really know how to differentiate that kind of say explosion from say standard binary sort of a neutron star coalescence or maybe a supernova and so on and so forth. So that's an interesting possibility, but yes, that's what I know.
Okay, Vahid says thank you. And thank you again, Misao, for the wonderful talk and also joining us at the late hour. Thank you very much.
So shall I just stop the sharing?
Yeah, stop share, and if I can ask Ranjan to share his screen.
Yes, I will. Can you see my screen?
Yes, and we can see your, yes, we can see your cursor. Okay. Well, we're very pleased to have Ranjan Laha. Ranjan, you have 25 minutes. I'll tell you when you have 5 minutes left. Begin your talk on transmuted black holes and neutrinos from gravitational wave sources when you're comfortable.
Okay, all right. Okay, thank you very much for the introduction. Thanks to the organizers for inviting me to this wonderful workshop. And I hope, and thanks to all of you who are attending this talk, and I hope all of you and your family members are staying safe and healthy during this pandemic. So today I'll be talking about two different topics. The first topic will be transmuted black holes, in which I'll try to show how observation of low mass black holes via gravitational wave mergers, mostly gravitational wave mergers, can lead to very strong, probably very strong constraints on particle dark matter interactions. And in the last half of my talk, I'll be talking about some brief overview of neutrinos from gravitational wave sources, and this is something which we can probably discuss in the discussion session. So before moving on, I would like to thank my collaborators, Anupam and Basudeb, for this work, which you can find in these papers. Anupam did all the work, and he deserves all the credit. And he's there in the audience. Okay, all right. So yeah, so that's the contents, and I'll first talk about transmuted black holes, and then I'll talk about neutrinos from gravitational wave sources. So before moving to transmuted black holes, let me talk about dark matter direct detection, more precisely particle dark matter direct detection. So I realize not every one of you may be familiar with this, so let me try to go over this step by step. So one of the best ways to detect particle dark matter is to look at a process called direct detection, in which you keep some target element, probably xenon, germanium, or maybe argon, at very low temperatures in sort of as background free environment as possible. And then you hope that a dark matter particle will come, will collide with the nucleus, and you detect the recoil of this nucleus. Right? You can also do it with electrons, by the way, but let's just talk about electrons, nucleus for now. The target is nucleus. In order to have a clean source, that is to have less backgrounds, we try to do it either under a mountain or in a mine. So that the process that we are looking at is dark matter plus standard model, most nucleus, going to dark matter plus nucleons, right? Nucleus. So this is what the typical event rate looks like. So what is being plotted on the x-axis is the recoil kinetic energy in keV. On the y-axis is the total event rate. If the dark matter mass is 100 GeV, right, depending on what is the target nucleus, whether it's xenon or germanium or sulfur, you see the recoil energy is at very low energy, right? It's a few tens of keV at the maximum 100 keV, right? So one needs detectors which can detect nuclear recoils at these very low energies in order to probe this kind of an interaction, right? So one can also do directional detection, in which one can detect the incoming direction of the dark matter particle, but I will not talk about that. Typically in these interactions, the direction of the dark matter is not, one cannot determine it. So this by itself is a very successful program, all right? And this is some of the latest limits. So what is being plotted on the x-axis is the dark matter mass, also called the WIMP mass in GeV. On the y-axis, the WIMP nucleon cross-section, all right? So this is the spin independent cross-section. That means we are assuming that the dark matter nucleon cross-section does not depend on the spin of the particles. So what you see, these lines, so these are upper limits. So that means anything corresponding to a line, anything above the line is ruled out, right? So for example, xenon 100 ruled out everything above this line, all right? So the latest limits are these ones, xenon 1 ton, this 1 ton here, this work, right? This is the limit, the black solid line. is the latest limit. There's also limits from Panda X, Xenon 1T, and Lux in 2017. All of these are very similar, right? So they ruled out a large portion of the parameter space, something going to slightly less than 10 GeV to many tens of TeV, and these cross sections. The minimum is something like few times 10 power 47, as you can see, right? So obviously this is a fantastic probe, and there have been lots of work on this thing. There's a future probe, Xenon NT, which is already being built, and this in 20-10 years of exposure can get this constraint, right? Again, anything above this line will be excluded, or you can discover dark matter. And finally, there's also this thing, this red line that you see is called neutrino discovery limit. So this is when neutrinos, so at this point, solar neutrinos, maybe supernova neutrinos, atmospheric neutrinos will form a background to this GX detection experiments. That means these neutrinos will coherently scatter with the nucleus and will form and will give a recoil, which is very similar to what the dark matter can do. There are ways to get around it, by the way. So we know using various targets, using detection to get around it. But anyways, it's a nominal thing which people sort of plot, and there can be many different physics things. All right. So once you look at this plot, there are a few obvious questions that you can ask. So two obvious questions is how to improve these limits. All right. So obviously one is build newer, bigger detectors. That's an obvious answer. And obviously our experiment colleagues are working on it. Well, the second question, but the question that we were asking is that, is there another way to improve the limit besides building newer detectors? Let's just as a complementary tool. The second question is, can we go below the neutrino flow to probe discovery space? Again, this is something which can be done using various different detectors, but we try to say if this is also possible to be done in a manner which we will talk about. So, sorry. Okay. Before moving on, let me first talk about low mass black hole discovery, or technically low mass compact object discovery, and then I'll try to connect both of these. You'll see how it connects. So this is a plot from this Northwestern website, which sort of shows the masses of neutron stars and black holes that have been discovered by LIGO Virgo collaboration or by electromagnetic radiation. As you can see, there's a wide range starting from slightly below 1 solar mass of neutron stars to as high as heavy as 160 solar mass black holes, right? And one can also look at all these, for example, look at this catalog, and one finds there have been lots of low mass black hole or compact object discoveries in the recent years, right? For example, in last year, LIGO announced this GW190814. In case you guys are not, in case somebody is not familiar with how to do it, so this is the date, 1408 is a month, 19 is a year, right? So that's how it, so that means this is a gravitational wave merger, which was measured on 14th of August, 2019, right? So this is a merger of something like 20 solar mass black hole with a compact object of mass 2.5 to 2.6 solar mass. Thompson et al. Announced a discovery of 3.3 solar mass black hole. This is not using gravitational wave, this is by using astrometry. Then there was GW190425, which is a compact binary merger where the total mass is 3.4 solar mass, and the component masses are between 1 to 2.5 solar mass. And finally, recently, there was GW200105 and GW2001. So sorry, so there's a typo here. So it's 15, where neutron star black hole mergers were detected, where the lighter component have masses between 1.9 and 1.5 solar mass, and these things, right? Note that probably these two are mostly neutron stars, but it's still useful to think what happens if these are black holes, right? So the questions that we were trying to ask is, what are the origin of these low mass black holes, right? So obviously there are astrophysical origins of these low mass black holes. There are primordial origins of these low mass black holes. People have as we just heard about primordial black hole talks. So the question that we asked, is there a new way to form these low mass black holes? In fact, and a related question is that what happens if you detect a lower mass black hole, right? And this last question is also a discovery topic for the LIGO Virgo collaboration. For example, they have this search for sub-solar mass black holes. There are already quite a few papers on this by the LIGO Virgo collaboration, where what they plot on the x-axis is the black hole mass. On the plot on the y-axis is the fraction of the dark matter in the form of primordial black holes. Anything that is shaded in this plot is ruled out. So this is from Ogle, Eros, Macho, Segway 1, Eritanos 2. The LIGO result is this one, this O2. All right, so anything above is ruled out here. And so this LIGO interprets this as a constraint on the primordial black hole parameter space. So what we asked, again, all of these questions are related, is what will be the implications of the discovery of a subsolar mass black hole? Or in other words, if you ever discover a subsolar mass black hole, is it guaranteed to be primordial? All right. Okay. So the answer is no, and this is what we discussed: transmuted black holes from dark core collapse. And this is basically this paper, if you want to look into it. So before doing this, let me talk about dark matter capture in compact astrophysical objects. This is a very old topic. It started even before 1985 by Press and Spergel. By 1985, there was papers even before this. The idea is as follows. Suppose you have a particle dark matter candidate, M chi. When it comes near to a compact astrophysical object, maybe sun, neutron stars, white dwarfs, it can maybe pass through the object. It can scatter with the nucleons in the target, right? It can also scatter with the electrons, by the way. Let's talk about nucleons here. Scatter with the nucleons target. Suppose scattering is such that it loses energy, such that its energy becomes less than the escape velocity, then the dark matter particle gets captured. All right. So obviously, as you can imagine, so this requires a non-zero dark matter nucleon cross-section, and this has been used for a long time, all right, to constrain dark matter nucleon cross-section via neutron observations, and also via the fact that we observe neutron stars. We observe neutron stars even currently in the universe, and the last part I will explain. However, what has not been appreciated, at least greatly in the literature, is what happens when a large number of dark matter particles get captured in the core of the star. Anyways, before this, let's talk about very briefly the capture rate. So this is a long equation. You don't have to worry about it too much. This is simple m sigma v with some factors taking into account the escape velocity, the dark matter velocity distribution, and things like that, the cross section, right? So it turns out that if dark matter particles are non-annihilating, then they'll keep on getting captured in the neutron star or the white dwarf. And then it turns out if the neutron star or the white dwarf is old enough, there'll be a lot of time where the dark matter particles will keep on getting captured. And it can so happen, depending on what is the cross section between the dark matter and the nucleus or the nucleon, the total number of dark matter particles that are captured inside the star can be greater than the number of particles required for a black hole formation. That means there are so many particles being captured inside the star. The dark matter particles inside the one which forms a dark matter core will collapse and form a black hole. Right? So there are scenarios which can do this thing. This has been studied in great detail in the literature. Now, this small black hole what happen is that it can be formed at the center of the star because of this dark matter core collapse, and then it can eat the entire star by just accretion. Right? So that means the small black hole which is formed at the center of the star, which has a very small mass, I mean something like 10 power minus 14 solar mass or 15 solar mass. This is for neutron stars. For other stars it can vary. This is formed at the center of the star, and then it can quickly eat up the entire star and form and make the whole star into a black hole. Right? So this is what we call a transmuted black hole. Right? So that means if you have a neutron star, say a 1 solar mass neutron star, the small dark matter core that's accumulated inside the star, it collapses, forms a dark matter, forms a black hole, and then the black hole eats up the entire star, forms a 1 solar mass black hole. All right, and then you can try to detect these things. Right. So the basic idea of this thing that I talked about was actually well known, and for example, this has been used to constrain again dark matter nucleon cross section. So what is being plotted here is dark matter particle mass and the sigma chi n, the cross section. So this region that you see excluded from this existence of PSR J04374715. So this is a nearby old neutron star. So this can, for example, undergo this process, and due to and the fact that this still exists tells you that dark matter cross section cannot be in this range. Right? So anything above there is ruled out. So these things are Panda X and Xenon 110 limits, these lines that you see. And this region tells you if the dark matter mass and the cross section is in this region, if the black hole that is formed inside the star, it will Hawking evaporate. So it will have no constraint. Right? So it's something like in this range. Right? So you can do this both for bosonic dark matter and for fermionic dark matter. So this M5 denotes the mediator mass. M5 denotes the mediator mass. And then, so this constraint, which comes from this PSR J0437, this depends on the local dark matter density. However, if you can find a process, say mostly via gravitational wave observations, where you see low mass black holes, and somehow you can exclude that, and somehow you can distinguish that from neutron star mergers or black hole mergers, astrophysical black hole mergers. And I'll tell you how to do that. You can probe parts of the parameter space. For example, suppose the dark matter density is 1 GeV per cubic centimeter. This is the region of parameter space you probe. Again, anything here we ruled out. It's 10 power 3 GeV per cubic centimeter. Here we ruled out. All right. This is the same plot, except this is for fermionic dark matter. You see there's a change in scales, right? It's simply because there's Pauli blocking here, and that changes some things. And there can be Bose-Einstein condensate formation here that will also change some things. Right? So we showed that if you find a low mass black hole, and if you can show that it is formed due to particle dark matter interactions, and I'll show you how you can distinguish various other possibilities later, then you can probe parts of the parameter space in dark matter nucleon cross-section, mass plane, which is not able to be probed by any other mechanism, right? Note that the neutrino flow is somewhere here, right? This line, I didn't plot it, but it's somewhere here, right? So this can go orders of magnitude below the neutrino flow. So the first question is, how do you distinguish this process from this transmuted black hole? Suppose you see a low mass merger, right? Say, suppose you see a merger of say 2.5 solar mass black holes, right? Very far away. How do you distinguish it between a transmuted black hole origin and a primordial black hole origin? The first thing, which is not a very robust thing, but still one can do it, is measuring the mass function, right? So what is being plotted in these plots is the mass of the compact object on the x-axis, number of observed neutron stars on the y-axis, and this is the number of observed white dwarfs on the y-axis. And if transmuted black holes are formed due to particle capture, dark matter particle capture, neutron star or white dwarfs, these are the two most compact objects, so there's more probability of forming transmuted black holes, then the mass function of these transmuted black holes should follow this, right? So note that we already know of subsolar mass neutron stars, and obviously we know of subsolar mass white dwarfs. So if you detect a subsolar mass black holes, that need not be primordial in origin. Right? So this is something which we pointed out. This was also pointed out by this paper by Takitsov et al., which appeared at the same time as ours. However, we also pointed out something else, which I think is a much better smoking gun signature, which is the redshift distribution of transmuted black holes. So let me explain this. So what is being plotted on the x-axis is the redshift. What is being plotted on the y-axis is the merger rate of various different things that we talk about. So taking neutron star merger rate, how it varies with redshift. So this is obviously there is some uncertainty, but this is a fiducial shape that we get. All right. Note that it peaks at around z equal to 1 or 2, because this is where the peak of star formation is. If you have primordial black hole merger, that's the other possibility. This will keep on rising like this. All right. Remember, at early universe, there is more dark matter. Dark matter is denser. In fact, dark matter is denser, hence the merger rate will increase, will keep on increasing. Whereas if you have transmuted black hole, the merger rate will follow this kind of a shape. And this, all right. Note that this depends quite strongly on what is the dark matter particle mass and the cross section. Note that this shape is drastically different from what you get from a primordial black hole and primordial black hole merger. Right. So that means if you see many subsolar mass black holes, or even slightly above black holes which has low mass, you can use this redshift distribution to distinguish between a TBH merger, transmuted black hole merger, and binary primordial black hole merger. Obviously, neutron star mergers can be distinguished by either using the electromagnetic components or by using their tidal deformation, or there can be other things which we'll talk about. Right. So note that this can only be done by upcoming third generation gravitational wave telescopes, for example, PDESICO, Einstein telescope, Cosmic Explorer, things that we'll learn about tomorrow in the talk. But the point is, this is actually a very interesting way, and this is sort of a smoking gun signature between transmuted black hole merger and primordial black hole merger. So we also tried to calculate what can, for example, an instrument like Einstein telescope measure. So what we did here is assume that the neutron star mass, the target neutron star mass, is either 1 solar mass or 1.3 solar mass. Assume that the particle dark matter mass is 10 power 4 GeV. The cross section is 10 power 47 to 10 power minus 45 centimeters square. Advanced LIGO will detect a small number of events, all right? So it depends on a few things. Obviously, advanced LIGO will not detect high redshift events because they are not that sensitive, but it can detect a few events, all right? Maybe one event every few years, right? Our Einstein telescope can detect a large number of these events, all right? Basically, we use this redshift distribution, and you can sort of do a very simple statistics of what is the number of detections at redshift z less than 1, what is the number of redshift detections at redshift z greater than 1, and what is the total. And you can use this to distinguish between between the primordial black hole scenario and transmitted black hole scenario. All right. So note that here, so given these numbers, advanced LIGO is already sensitive to dark matter parameter space. Say for example, again, 10 TeV dark matter mass, 10 power minus 45, 46 centimeters square, which are not ruled out by any present data. All right. So one can actually do this exercise, which we are doing now, to see what kind of parameter space gravitational wave observations can probe. All right. So this sort of ends the first part of my talk. I will go to the next part, which is a bit completely different, which is neutrinos from gravitational wave merger events. So note that I'll be talking about, I'll not be talking on the behalf of IceCube or Antares or Pierre Auger collaboration. I'll be talking about somebody who has worked on neutron astrophysics a bit.
Ranjan, this is you have perfect timing. You have 5 minutes left to cover this last part of your talk.
Yeah, this is just 5 minutes there. Thank you. All right. So let me first start with GW170817. Right. So this is the first neutron star binary neutron star merger system that we have observed. This was located at a distance 40 megaparsec from us in this galaxy, NGC 4993. This was detected in both gravitational waves and electromagnetic waves, UV, optical, and IR. However, it has long been speculated, and this happened even before this merger, that binary neutron star merger systems or even neutron star black hole merger systems can be very good regions for particle acceleration, right? Charge particle acceleration, cosmic acceleration. And these are completely astrophysics things. And if you have charge particle acceleration in these regions, you must produce neutrinos, right? You just cannot stop it. The way you produce neutrinos is this process. So you basically accelerate, say, protons. You can also accelerate nucleons, by the way. Let's just think of protons for simplicity. You accelerate protons. It can interact with the target photons, which is nearby, or even the target material. And then you have all these hadronic interactions to produce neutrons or pions, which will produce neutrinos. Right? And this, if you ever detect these neutrinos, it will tell you that these sites are also sites where hadronic acceleration happens. Right? So let me briefly talk about. So this is an old slide I've taken from Brian Metzger's talk, but this actually we have taken it from these two papers, which talked about how neutron star in spirals or neutron star black hole in spiral can form either a neutron star or a black hole, or in the black hole in this case. And the particle acceleration typically happens when you form a black hole and you form an accretion disk around it, and the particles get accelerated near that region. Or sometimes there is material which can fall on top of the black hole, and that undergoes particle acceleration. And once you undergo particle acceleration, it's almost guaranteed that you'll produce neutrinos. This is something which was searched by various neutron telescopes, IceCube, Antares, Pierre Auger, during GW170817. Right. So what is being plotted on the x-axis is the neutrino energy. Being plotted is the neutrino flux, E square F. This is fluence per flavor. All right. So nu x plus nu x bar, right, per flavor. So if you look at a region at a time 500 plus minus 500 seconds around the merger, so these are the upper limits from Antares, IceCube, and Pierre Auger. And these lines that you see from Kimura et al. So these are what was being predicted. Right. Note that the fact that we did not see neutrinos in this for this thing was sort of expected. First of all, this was an off-axis GRB, right, and this was also a low luminosity GRB. Right, so it was expected. There are other models. For example, there's this model by Fung and K. Fung and Brian Metzger, which predicted neutrinos for a longer time. So that's why they searched for neutrinos for 14 days after the merger, and they did not measure it. And this, again, it was also expected because this event, at least for neutron telescopes, this event was quite far. For electromagnetic telescopes, for gravitational wave telescopes, it was super close, but for neutron telescopes, it was quite far. But this is something interesting to look forward to, and I hope we will have some discussion in the discussion session on it. Okay, so I conclude my talk. So my first part of my talk was BSM physics, where I talked about how dark matter particles can accumulate inside compact astrophysical objects and produce low mass transmuted black holes. This is a compelling alternative to primordial black holes. I hope I have been able to convince you, both for sub-Chandrasekhar and sub-solar mass black holes. The way to distinguish between primordial black holes and transmuted black holes is the redshift dependence. This is really a smoking gun signature. This requires either Einstein telescope, cosmic explorer, or something else, pre-Desigo or Desigo. Or you can also look at mass dependence of the population of low mass black holes that we see. We can distinguish this thing. And finally, I talked about some standard model physics, neutrinos from compact object mergers. And these are an important target for neutron telescopes. And they'll actually tell you whether compact object mergers are regions of time, are regions where cosmic ray acceleration happens. At least hadronic cosmic ray acceleration happens. Thank you.
Okay, thank you. And you're even ahead of time. So well done. We have a question from Cecilia Lunardini. Could sub-solar black holes also be produced by fast evaporation of supersolar astrophysical black holes?
Okay, thanks. So this is a good question. So the question, let me just repeat. So effectively, the question is being asked, so if you have astrophysical black holes, can they evaporate and produce subsolar black holes? The answer is no. That's simply because Hawking radiation is just not effective. Hawking radiation is very effective at low mass black holes, 10 power 14, 15, 16, 17, at the most 18 grams. But for astrophysical black holes that we see beyond a few solar masses, Hawking radiation is just too weak. And also the temperature, actually, the other thing is the temperature is less than the CMB temperature, that also agreed. So yeah, you just cannot produce subsolar mass black holes using Hawking evaporation of supersolar mass black holes. Yeah, thanks for the question.
Any further questions? If not, I was wondering what sets these mass functions for these two different astrophysical objects you look at, because they have slightly different distributions. I'm wondering what exactly sets their structure.
This one?
Yeah.
Yeah, okay, so this has to do with stellar physics. To be honest, I really don't know the complete answer. So remember, so this basically comes out from how do neutron stars and white dwarfs form. Right? So this is the basic. So neutron stars are typically formed from core collapse supernovae, right? Stars which have a mass greater than 8 solar mass and less than something like 15 solar mass. When they go supernova, they will form neutron stars, right? So that's why they are slightly heavier. Note that this also depends on a few nuclear physics. Whereas white dwarfs are formed from lighter stars, right? So there, these stars cannot form, for example, the iron core at the center. Hence, they cannot go core collapse supernova. So that's why they have less mass, as you can see. The mass functions are different. They have less mass, and they can also go to much lighter masses. So this is the basic idea. Basically, these are okay. One sentence answer. These are formed from neutron stars are formed from hotter stars. White dwarfs are formed from lighter stars or cooler stars. So that's the difference. So they can form, these can form iron, these cannot form iron. So that's why they can go to higher masses, these cannot. Plus there's some nuclear physics, and maybe Chichi can actually say more on these things. She's an expert.
Okay, so given the time, maybe we can leave that for the discussion session later on. And I'll thank you again for your very nice talk.
Thank you very much.
I'm going to ask Konstantinos to share his screen. So if you can stop sharing yours, Ranjan, when you have time.
I've already stopped sharing.
Ah, okay.
Oh, it must just have taken a moment. Okay.
Mm-hmm. So,
okay, so we're very pleased to have Konstantinos Skordis talking about constraining non-GR gravity scenarios with observations of gravitational waves. And I can see your slides. They're in full screen, and I can see your mouse. So, well, in fact, can I see your mouse? Can you wave your mouse around?
Does it show?
I can't see your mouse.
Just 1 minute.
So one thing you could do if that was Keynote, you could export it to a PDF and for some reason.
do have it in PDF. Just give me a second. I'm gonna try again. Just quit some other things. Okay.
Yep, we can see the mouse. We can see your slides.
Okay. So let me go into full screen just to.
It's just taking a moment to go into full screen.
Yeah. Sorry.
No worries. I mean, you can always start just whenever you're comfortable.
Yeah. Okay. So everything visible?
Yes.
Okay. So thanks very much for the invitation. It's a very nice meeting. And what I will be talking about today is about constraining non-gravitational waves. So before talking about what we mean by non-GR, let's talk about GR itself. So GR is our best known theory of gravity, and it has been very well tested in the strong field regime, like a solar system or binary pulsar. So in fact, what I'm showing here is the table of parameterized post-Newtonian parameters taken from Clifford Wills' Living Reviews review. And what we see is that all of these parameters have been measured to have values which are essentially centered around 0, which is the value predicted by general relativity. So the limits around them are tiny, 10 to the minus 3, 10 to the minus 4, or even much smaller. So why should we even think about other theories of gravity which are non-general relativity? Well, we do have some very strong motivation, which goes under the name dark sector. So the dark sector has to do with the observed cosmic acceleration and the observed dark matter phenomenon. Now, the observed cosmic acceleration is most simply explained by a cosmological constant. And the dark matter is mostly simply explained by particles. In fact, we don't even need to worry about what is the underlying particle description. Cosmologically, all we need to care is about solving the Boltzmann equation. So things get very much simplified. Now, of course, there are alternative ways people have thought of over the years, and that is to use coherent fields. So in the case of cosmic acceleration, people have talked about quintessence or k-essence or all sorts of different types of scalar fields, which are disconnected from the other matter sector. And in the case of dark matter, we talk about ultralight axions as coherent fields. Now, in all these cases, we basically have to do with new degrees of freedom. So the fact that we have a dark sector implies that we must introduce some sort of new degrees of freedom. But of course, still, what does that have to do with gravity? Before even thinking about that, essentially introducing non-GR gravity means that we must have new degrees of freedom. So this is comes from Lovelock's theorem from 1967, which under some general assumptions says that if you want to write down a theory which is non-general relativity quite generically, you must have new degrees of freedom. So the question that people try to investigate is whether the dark sector degrees of freedom that we must have are in fact due to gravity. But of course, I showed very strong constraints on GR, on gravity actually, away from GR due to the parameterized post-Newtonian parameters. So let's scrutinize those a little bit more. And what are we testing with those parameters? So here I'm showing a plot which is plotting the curvature versus the potential over a wide range of magnitudes and for a large number of physical systems. So here you can see, like, this line is the planets of the solar system. Here we see stars of the Milky Way, yes, stars in the center. We have pulsars here, white dwarfs, neutron stars, black hole. This is the horizon of a black hole. And down here we have other objects like galaxies, CMB peaks, clusters, and cosmological constant is right here. So this is quite interesting because in all the places that we have actually very much tested GR, they lie here in the higher curvature regime. So this is where we see deviations at most 10 to the minus 4 to 10 minus 8 level. So we don't have any evidence of non-GR behavior in this case. So if there are any gravitational degrees of freedom, they have to be completely suppressed because we don't see them. But if the dark sector is due to new degrees of freedom in the gravity sector, they will appear down here, and that's the case where they are very much alive. So we haven't tested this thoroughly, and this is where things can be pretty much going on for explaining the dark sector. So let's talk about now more about gravitational waves. So starting from GR, in GR we have one gravitational degree of freedom, one graviton, which is spin to field, and it obeys the usual transverse traceless conditions. So it comes with polarization of plus and minus 2, displayed here, and it has been detected by LIGO. So we know that this is there. Its mass is predicted to be 0, but the actual constraints, experimental or observational constraints, are in the range of 10 to the minus 22 to 10 to the minus 32 electron volts, depending on which method has been used to constrain it. So you can see a very broad discussion of these methods in this paper here. And finally, the speed of gravity is predicted to be the same as the speed of light. And this has also been measured by the advanced LIGO and Virgo detectors in combination with electromagnetic probes. And we now know that the deviation from 1 is less than 1 part to 10 to the 15. So it's very well constrained to be equal to the speed of light. Now, what happens if we have gravitational waves in non-GR gravity? So first of all, we have many more polarizations because these are the different polarizations which are allowed by the curvature tensor. So apart from the 2 tensor modes, which are going to be there, we can also have 2 transverse vector modes, so plus and minus 1 polarization. And we can also have 2 scalar modes, the so-called breathing mode and the longitudinal mode. Of course, this is the massless tensor mode which has been detected. But in addition, we may have additional massive tensor modes in the case of massive gravity, which don't necessarily couple to matter. And also, in addition, each scalar vector or tensor mode may also move at different speeds, which are not necessarily equal to the speed of light, and it can also have different masses. So LIGO has not detected these other types of polarizations, and so we don't know what the speed is going to be or what is the mass of these other modes. Okay, now let's focus on the speed of tensor modes, which has been measured. It's a very simple calculation. We see an event which is about 40 megaparsecs away, coming from a neutron star merger. So it emits gravitational waves, tensor modes, and photons. We detect them on the Earth, measure the detection time, and we find that it came within 1.7 seconds apart. Now, of course, there are many astrophysical uncertainties which could make this bigger, but it's not big enough to make a big difference. So if we just divide the difference in time with the distance, we get a very, very small number, which is 10 to the minus 15. So it doesn't matter if it's 10 to the minus 14 or 13, it's still extremely small. So we safely assume that it is exactly 1. Here, this alpha t is something which is called it's one of the effective field theory of dark energy parameters. So you're going to see it quite a lot in the few minutes, along with some other parameters. So what LIGO measures is that this is effectively 0. So how is this calculation done? You just take a Freeman-Ropes or Walker metric, you put a graviton on it, a tensor mode, and then you find the propagation equation in some generic way. And so this is how it looks like. We have now here 3 parameters. Here is the alpha t. We have something else called alpha m, and some other mass scale, which can appear in the coupling to matter. This can be done in some generic way. So we can then run this and measure this alpha t. Now, the interesting thing is now to compare with theories, because there have been plenty of theories proposed to explain cosmic acceleration. A very popular one is called Hordesky theory, which is in fact some general way of describing other types of smaller theories, like Brans-Dicke theory is part of Hordesky, Galileon's so-called Fab4, chameleon symmetros, and so on. And what this thing is the most general scalar tensor theory with second-order field equations. It has one additional field, phi, apart from the metric, and it comes with 4 free functions. And these free functions, G2, G3, G4, and G5, depend on the field phi and its kinetic term x. And they are completely general up to some conditions so that it's ghost-free and all that. Now, what we want is Lorentz violating background. So this phi dot is not 0, and we expand around the background. And to have cosmic acceleration, we need the contributions from these additional terms to essentially be quite close, some effective cosmological constant plus some time-dependent corrections, which are not very large. Okay, so once we have this theory, we can in fact calculate what is the alpha t. And this is the expression. It is proportional to terms which come only from the G4 and G5. So G2 and G3 have no contribution whatsoever to alpha t. And so they are not constrainable by the speed of tensor mode only. Of course, a trivial case, if you want to set this to 0, you just assume that since the derivative of G5 with respect to phi and x have to be both equal to 0, you assume that G5 is simply 0, so it's not there. And G4 has to be only a function of phi. And if this is satisfied, then you get a set of viable theories which are in line with the LIGO data. Now, you can also be a bit more devil's advocate and say, look, we only saw one event, Redshift is 0. So what we should really be doing is running a set of models and making sure that only today alpha t is 0, because strictly speaking, alpha t is time dependent. So you can start with some non-zero value of alpha t in the past, and then eventually you just get down to 0. So this was done by Schiaga and Zumalaccarregui. Here, what they show is the case of pure Galileons. So first of all, the cubic Galileon sits on this point here because it has alpha t equals 0 and is compatible with CMB. And then there is a quartic Galileon compatible with CMB, which is this blue line here, and the quintic Galileon, which is the green contours. Now, in these cases, the quartic Galileon is ruled out by alpha t being 0, so that's gone. While to rule out the cubic, you need to also consider the cross correlation between CMB and large-scale structure, which rules out this gray shaded region. So what is left is some fine-tuned models of the quintic, which lie exactly on this line here, this black curve, which is black line here. And those start with some initial conditions and end up with alpha t equals 0. But strictly speaking, those need extreme fine tuning and are very likely to be ruled out by any other similar event at a different ratios. Now, of course, you can say, well, okay, this is a trivial case, but hang on, there is a phi double dot sitting here. And phi double dot means that we can't simply choose phi double dot to be determined by its equation of motion. It's a second order theory. So we take the equation of motion for phi double dot, so we solve for it, and then we plug it into this expression. And only after we do that, we should then try to see what are the viable models which remain. So this is a non-trivial case. This is exactly what we did a few years ago. So you take the equation of motion, you plug it in, and you find that alpha t is now proportional to some set of coefficients, let's call them Cij, which depend on phi and x, times powers of Hubble parameter and its first derivative. And you want now to set this to 0 for any general cosmology. This means that you need to essentially set the coefficients to 0, because you want this to be 0, not for fine-tuned cases, but for any general cosmology. Once you do that, you discover that indeed there is a non-trivial case which survives and has a quintic part and a quartic part. So now there is a G5 of x and a G4 of phi and x, which survives, plus some other terms which involve G2 and G3, but they are not relevant for gravitational waves. Now, this was done for a flat universe, but if you include curvature, then you get additionally at some other terms. Let's call them Dij. And so to have this equal to 0 in a curved universe, it turns out, so you need, first of all, to have the Dij to be equal to 0, but the D01 component of this matrix here is 0 only if G5x, x equals 0, which essentially kills this non-trivial case. So we're back to the trivial case as the only survivor. Now, okay, why do we want to have curvature? You can just say, we have inflation, it's a flat universe, why do we even care about curvature? We do care about curvature because if we have inhomogeneities, then those inhomogeneities behave on the average as curvature. So in principle, we would expect that if we let the gravitational waves propagate through an inhomogeneous universe, then that might have an effect which would also kill this non-trivial model, even in the flat case. So this is what we've done. This is a picture of some schematic picture of inhomogeneous universe. So what we want to check is what happens when a tensor mode propagates through FRW as compared to propagating through different inhomogeneities on the way to us. Okay, so this is the model we assume. We take a perturbed Freeman-Robertson-Walker metric, and it has potentials phi and psi sitting here. And on top of that, we include a gravitational wave, which is a small perturbation, much smaller than the potentials, which are themselves at least 10 to the minus 5. Okay, you can even make sure that this is the case. Indeed, if you take the ratio of Hij to phi, you find that it's something like 10 to the minus 17 times 40 megaparsecs over the distance. And so this is indeed a very small number throughout most of this propagation, except when you're very, very close to the source. Okay, so now we can calculate what is happening. You start with the theory in question for Hordetsky. You have to plug in this particular metric unsunks. Of course, you get a horrible, complicated set of equations, but we can be a bit smarter and see what exactly we are testing. So first of all, we are only interested in LIGO wavelengths, so it's about 1,000 kilometers. And we are also only interested in large-scale structure inhomogeneity, so bigger than 100 megaparsecs. So the small number that we have here is the ratio of the gravitational wave wavelength over the size of the structure, which is 10 to the minus 18. This essentially sets up a hierarchy of scales. So we can assume that derivatives of potentials goes as phi over r, derivatives of gravitational waves goes as h over lambda. And so we can calculate the different possible terms which could occur into the field equations. And we find this particular hierarchy. And what we essentially need to keep is simply derivatives of h. But when we encounter derivatives of potentials, we can safely ignore them. And also when we encounter terms which have to do with potential times derivatives of h, we can also ignore them. And this is what comes out. We get a similar tensor mode equation as before, only now the time derivative part is multiplied by 1 minus 2 psi, which is the G0 part of the metric. And the spatial part is multiplied by 1 minus 2 phi, which is the spatial part of the metric. Effectively, this means that the gravitational wave is propagating in a background, which is set by this perturbed FRW background. And so there is an effective metric, which is given by these two potentials.
You have 5 minutes, Konstantinos.
Okay, thank you. I'll try to speed up. So you can plug in the numbers, you find this alpha t. It does come out to be proportional to grad square phi plus other terms. And indeed, when you put in the numbers, you find that this is 10 to the minus 3, which is much, much bigger than 10 to the minus 15. And therefore, these non-trivial cases are indeed ruled out by large-scale structure. Now let's talk a little bit about beyond Hordesky. Beyond Hordesky is essentially Horndeski plus some additional terms. First of all, you allow third order field equations, which have additional constraints, removing degrees of freedom. And apart from the 4 functions that I mentioned before, you have 2 additional functions called F4 and F5. There is a new EFT of dark energy parameter, alpha h, which depends on these 2 functions and is proportional to them, but no derivatives of them. And again, you can plug in into alpha t equations. And in the trivial case, you find a set of relations. So first of all, the quintic term is not absolutely ruled out, but there are some surviving terms. They have to simply satisfy this relation between F5 and G5, and similarly for F4 and G4 and G5. So there is a bit more freedom here once you allow for beyond Hordesky. You can also play the non-trivial case game. So you have a phi double dot sitting there into the alpha t function. You plug in this equation of motion, you find the set of coefficients that you have to set to 0. And I'm not going to write the cases down because it's quite long, but you do get a lot of non-trivial cases which do have non-zero functions and do give alpha t to be exactly 0. Okay, very good. Assume now that alpha t is 0 and you have some of these beyond Hordesky theories. What else can you do? Well, this was investigated by Creminelli and Bernizzi, and they looked into the fact that because you have a Lorentz violating background that you're expanding on, it is possible to have the tensor mode decaying into the scalars because of the breaking of Lorentz invariance. Essentially, this is the interaction term, which is responsible for the decay. So let me speed up a little bit. They do calculate the transition rate, which comes out to go as momentum of the gravitational wave to the 7th power. The speed of the scalar mode does enter here. And then there is a scale, lambda star, which comes out of the theory. So it's something that you calculate by canonically normalizing the fields, the metric and the pi field, which is a perturbation to the scalar. And it does enter in this transition rate. Now, interestingly, there is another scale in the theory called lambda 3, which if you want these things to have anything to do with dark energy, then this scale, just out of coincidence, nothing more, comes out to be similar to the LIGO frequency. So the momentum from LIGO is about 1,000 kilometers to -1, and it's similar to this lambda 3 scale. So In addition, we want this rate to be smaller than the Hubble rate, so that the gravitons, because we have seen gravitons, so they're gravitational waves, so therefore we cannot allow for them to have decayed on their way to us. And so by replacing P with λ3, what we find is that this lambda star must be much bigger than λ3 for this to be viable. And both of these are coming out of the theory now. They're parameters of the theory. Translated into this beyond Hordesky parameter, it says that this alpha h, which is non-zero only in beyond Hordesky, has to be much smaller than 1. So what we're seeing here is that beyond Hordesky theories are completely ruled out, even if they predict alpha t equals 0, because of decay of tensor modes into scalars. And we have seen the tensor modes. Okay, so beyond Hordesky is ruled out. And the only surviving case is this particular Lagrangian. So we have a G4 phi times R plus G2 phi X plus G3 times box phi, which is like a cubic term. Nothing else can go through. And before finishing, just a word of caution. All these constraints which I have presented assume that effective field theory is valid all the way to LIGO scales. But as I have shown, the strong coupling scale, which is part of the theory, is just by coincidence similar to the LIGO frequencies. So this is quite questionable now. How can we use LIGO data to test these theories within effective field theory? So this was investigated in this work here. And while they don't come with an answer, they do show that there are toy models where you can have a speed of the new degree of freedom, which is significantly different than 1 around Hubble scales. But then it does turn around on LIGO scales and becomes equal to the speed of light. So this is a possibility. Unfortunately, we cannot answer whether a UV completion of some beyond Hordesky theory has similar behavior, because we don't have UV completion for these theories. So that's something to keep in mind. So I will conclude here. Same method, different theories. This is just a list of other theories which I have not discussed, and what is ruled out and what is surviving. I can just very briefly go through it. This is the only surviving DOST, or degenerated higher order scalar tensor theory, which is a generalization of beyond Hordesky. So there are these free functions surviving. This is the only thing which can survive both the alpha t equals 0 and gravitational wave decay. There's I-star ether theories, the generalized Proca theories. Tevez theory was considered for the case of dark matter that is completely ruled out. And this is the only surviving case down here. So to conclude, the recent gravitational wave detection plus electromagnetic counterparts have had a tremendous impact on theories beyond GR. It has grossly limited the parameter space of the dark sector, and more events will get rid of the fine-tuned cases. A few interesting theories do survive, though, that can be studied further. And just to flag this here, my wish list, which is all these theories do predict other types of polarizations for gravitational waves. So it would be very interesting to see constraints on those other polarizations. Okay.
Okay, thank you very much for updating us on the status of these non-GR theories. Do we have any questions or comments? If we don't, or if people want to ask questions in the discussion session later, I would encourage that, because we're almost 10 minutes behind time. So I'll thank you once again, Konstantinos, and ask Michael to share their screen, please.
Sure.
Thank you.
Thank you.
Let me go ahead and do that. You can hear me?
I can hear you. I can see you. I can see your slides and your mouse. Excellent. So we're very pleased to have Michael Federke talking about bridging the gap between the microhertz, bridging the microhertz gap with asteroids. So please go ahead when you're ready.
Great, thank you so much. And thank you to the organizers for the opportunity to speak today. So I'll be telling you about some work I'm busy finishing up with Peter Graham and Sujit Rajendran, trying to think about ways in which we can try and detect gravitational waves. So this is more gravitational wave detection talk in the sort of band between PTAs and LISA, and kind of trying to do it in sort of a fun and sort of offbeat way, trying to utilize asteroids as test masses for a gravitational wave detector. So I'll tell you a bit about this proposal and how we think we can go about doing that. Just to zoom out though, just think very broadly about the gravitational wave parameter space we're trying to look at. We have this enormous range of frequencies we can try and think about detecting gravitational waves in, and there's a very strong science case from down below microhertz up to kilohertz frequencies. We have detections already between a hertz and kilohertz from Virgo and LIGO, and with Calgary coming online now as well. Around a millihertz, LISA is a very well-developed proposal. LISA Pathfinder is already flown, so we know how to do gravitational wave detection here, and hopefully future facilities will be able to do that. Tianquin is a more recent proposal here. And then down at nanohertz frequencies, we have pulsar timing arrays, including some interesting recent hints from Nanograv. Also, I'm not shown on this plot, but what has attracted a lot of attention in recent years is this band between LISA and LIGO, the so-called midband, where there's been a lot of work in recent years trying to address this band using atomic interferometry techniques or clock-based techniques. And I'm sure we've heard a lot of talks about that already at this conference, and there'll be more tomorrow. So I'm not going to spend much time talking about that because I think that's been very well developed in the last few years. What I'm going to focus on, however, in this talk is this other glaring gap in this plot, which sits between PTAs and LISA. So this is a much less well-addressed gap, and there's been much less study of how you might go about doing gravitational wave detection in this band. There are a number of studies that have thought about this using astrometric techniques from survey data trying to access this band. And there's been sort of one study that we're aware of in the literature, which has sort of tried to address actually entering this band in more detail. So let me just briefly speak about that, this so-called MUARES proposal. So the MUARES white paper, which is this reference here, basically tried to make this the case that there's a very strong science case for trying to access this frequency band between PTAs and LISA. And they have here a number of sources they identified as interesting potential science targets at levels of strain sensitivity which would not be accessible given existing projections for either LISA or PTAs. And I've just listed some of these here. I won't go through all of them, or actually any of them, just to flash this up to say there's interesting science to be had trying to access levels of strain which are currently inaccessible by other proposals. What the MUARES white paper also showed was what they call the straw man mission concept, which was basically trying to sketch out the technical requirements that would be needed in order to access this band using something like a LISA-style detector using larger baselines and better test masses, and I have some more to say about that in a moment. And it turns out, actually, it's kind of singularly difficult to build a gravitational wave detector right in this band around a microhertz. So let me spend a little bit of time talking about why that is the case, because it's going to lead me into a motivation and a question which will lead us into why we think that asteroids are a good way of trying to access this band. So let's think about trying to attack this band from both sides. So from high frequency going down, you'd be using something like a LISA-style detector where you're doing some sort of local test mass-based gravitational wave detection. Here, of course, you're sort of very approximately flying satellites that have drag-free test masses in them, and in some sophisticated way measuring the distance between those test masses by sending light across the baseline and trying to measure the variation, the light travel time in more sophisticated ways, of course, than just doing straightforward ranging. But the thing that limits you in trying to do this sort of local test mass-based gravitational wave detection, if you're trying to push into the microhertz band, is ultimately what perturbs your test masses away from being good perfect traces of geodesics and GR. So the thing that limits your sensitivity of these local test mass-based approaches is the so-called environmental or acceleration noise in your test mass. And so just to take one example, LISA Pathfinder has already flown, demonstrating sufficient test mass engineering to achieve LISA's goals. So here's the LISA Pathfinder acceleration amplitude spectral density plot, which achieves brilliant results, particularly around a millihertz to 10 millihertz. This easily exceeds the LISA requirements. But you'll notice here that going to lower frequencies, they suffer from this rising 1/f noise, which translates into a very rapid cutoff of the frequency sensitivity of LISA below, say, their most sensitive band. So although LISA is doing extremely well between millihertz and 10 millihertz, going down to lower frequencies, by the time you're at 10 to the minus 5 hertz, you've already lost 5 orders of magnitude in sensitivity. So this cuts you off quite dramatically, trying to use these local test mass-based approaches, trying to get into this low frequency band. So what MUARES was basically was saying in their straw man mission concept was, well, how can you use this kind of technology to get into this band, and just sort of sketching out the technical requirements for this. So the first thing it did was say, well, you can use much larger arm lengths. Of course, you win on the strain just by going to a larger arm length for a fixed acceleration noise. And they were saying you can use something like a 2AU baseline, which is about 100 times larger than LISA. That has technical difficulties associated with it, which are something needs to be addressed as well. And they also said, well, the thing that we would also need was to be able to engineer better isolation for your test masses. So what they assumed was basically LISA pathfinder sensitivities, but extrapolated down to lower frequencies. So that is some significant improvement in the technical ability to isolate your test masses from environmental noise. So this is sort of an estimate, gives you a flavor of the technical challenges associated with trying to push this local test mass-based detection into the microhertz band. The other thing you can try and think about doing is just use much larger test masses. So LISA uses, for instance, a 2 kilogram methyl cube. What if you could use much larger test masses? Now, of course, you can't necessarily fly very large test masses from the ground, but this idea of, large objects, and here I mean astrophysically large objects, being stable to external perturbations kind of underpins in a slightly different sense the other way to try and access the microhertz band, and that's using pulsar timing arrays. So if you're trying to think about getting into this band from below, going up in frequency, what you're looking at is pulsar timing array sensitivity. And here you're using pulsars, which are both excellent test masses because they're solar mass objects, but they're also excellent clocks. It's very difficult to perturb the rotational state of a solar mass object. And so you can potentially try and think about using PTAs to access this band as well. But of course, PTAs also suffer from the fact that they're losing sensitivity going into this band because they're scaling linearly in frequency as you move to higher frequencies. And also you get cut off at some frequency from your sampling rate. So for a fixed sort of timing residual for a PTA, the levels of strain sensitivity achievable right around a microhertz for PTA are not at the level where you would be trying to access some of the interesting science targets that the MUARES white paper was identifying as potentially things you might want to go after. So in some sense, you're kind of stuck between a rock and a hard place. Trying to access this band from above, you're stuck with your severe acceleration noise on human engineered test masses. And from below, you're stuck with basically a limited ability to measure timing residuals and pulsar timing arrays. So very, very roughly on my matrix of things that are challenging to get into this band, you can sort of summarize the situation as shown up here. But looking at this little table, you can kind of pick out, well, what if we didn't focus on the negatives and focus instead on the positives here? So LISA style detection, where we are able to engineer the ranging link or the way of measuring where the test masses are, is easily good enough in the microhertz frequency band to not be a problem. On the other hand, things like PTAs, which use astrophysically large test masses, don't suffer from the kinds of acceleration noise problems that human engineered test masses that you can actually fly from the ground would suffer from. So this leads us to ask the following question. Is there some way in which we are able to utilize astrophysically massive natural test masses, but do it in such a way that we are able to engineer and build the ranging link? Now, of course, I'm sort of burying the lead here a little bit. What I'm going to try and argue in this talk is that asteroids are an appropriate class of test masses to go after for this. They're very large objects. They're much more massive than anything we can possibly fly from the ground into space. But they're also nearby. They're not, these are not pulsars where there's no hope of ever getting anything there to build a ranging link. These are things which are in the inner solar system. And so it's entirely plausible that you can fly a mission to an asteroid and actually place on the asteroid some sort of human engineered apparatus which can serve as the ranging link. So just to be very concrete about exactly what I'm going to be proposing and talking about here, what I'm going to try and do is say, let's identify some good asteroids. So let's say this is 433 Eros, and this is another asteroid which is Bennu. Actually, this would not be a particularly good candidate for this because Bennu sort of throws rocks off its surface under rotation. It's a bit of a rubble pile, but it's got a nice picture, so that's why it's on the slide. And the idea is, so once you've identified appropriate asteroids, what you would do is you would fly a space-based mission, which would park on each asteroid a base station. That base station consists of a local space-qualified atomic clock and an emitter-receiver station, which can send out electromagnetic radiation and receive it, either laser or radio. And then the idea is you do something quite similar to lunar laser ranging, except you're not perturbed by the atmosphere or anything like that, and you're just ranging between these asteroids. So the asteroids here are serving as the test masses, and we're going to park base stations on these asteroids and utilize these base stations to send pulses back across the baseline to time the pulse return time and trying to utilize this as a gravitational detection concept. So just to briefly outline that I'm not talking about science fiction here, asteroids that are in the appropriate class, which turn out to be asteroids which have a diameter of, say, on the order of 10 kilometers and are in the vicinity of the Earth. They don't need to be near Earth asteroids, but they can't be things in the asteroid belt. These asteroids do exist. So here's just a random selection of them. I'm not necessarily arguing that these particular ones would be the ideal candidates, but these are just a couple that we found in the NASA JPL small body database. These asteroids also have rotational periods of a few hours, which puts them at about 30 microhertz, which is actually above our band, which will be important, as I will show you in a moment. And the other thing, which is not science fiction, is the fact that, flying missions to asteroids is something that has been done, and people have actually landed on asteroids at least 5 times in the last 20 years. So here's just a selection of various missions and the years in which they basically did the rendezvous with various asteroids. And you can see here, like we've landed things, we've done sample return missions, even Hayabusa 2 had little rovers which hopped on the surface. And you can even see this little video here from OSIRIS-REx actually doing its sample collection off the surface of Bennu. So, this is not beyond the realm of human engineering technology at the moment to achieve missions to asteroids. So asteroid candidates of the appropriate class exist, and missions to asteroids are ongoing. So with that caveat out the way, let me briefly step through why we think asteroids are actually reasonably good test masses for this kind of proposal, and why they would not be kicked around too much by environmental perturbations. So I need to walk through a couple of estimates for various noise sources to try and demonstrate to you that asteroids would be appropriate test masses for doing this. And what I'm going to so I'm going to ignore things obviously like large things so planets and moons in the solar system, which obviously are going to pull any inner solar system test masses around. The locations and GM of these objects is very well known. You can model those out of the data stream. The things that actually are important to think about are stochastic fluctuations, and in particular solar fluctuations associated with either the intensity of the solar wind or thermal cycling effects on the asteroid will be important to consider. So I'll step through a couple of those estimates. There'll also be very strong noise at the rotational period of the asteroid, and at very low frequencies, actually a point we made in some work at the end of last year, there's a stochastic noise from the other asteroids in the solar system, which is going to limit you. And then there are a bunch of other things we've checked. I'll say some words about seismics because we think there's a developmental goal here to achieve in future, but we've checked a bunch of other things as well, and these don't appear to be problematic. At least they're not dominant noise sources. And then toward the end of the talk, if I have time, I'll briefly say some words about link noise and clock noise as well. So let me start going through the solar intensity fluctuation noise estimate in some detail, because this sort of sets the pattern for how these noise estimates go. And then I'll step through the remainder of these somewhat more quickly. So we think about solar radiation pressure on an asteroid. Let's take a Strawman asteroid, which is an 8-kilometer radius asteroid with roughly the density of large rocky asteroids, and say it's located at 1.5 AU from the sun. The DC acceleration that you would find on an asteroid of that size and distance is something like 10 to the minus 14 meters per second squared. Now that sounds small, but if this were relevant noise in our frequency band, it would be about 3 to 4 orders of magnitude too large an acceleration to be able to access interesting levels of strain sensitivity. But of course, this is not the relevant estimate for the background that you're trying to fight against, or the noise you're trying to fight against in the relevant frequency band, because this is just the DC force applied by the sun. What you really care about is the temporal variation of this that has frequency content that overlaps with the microhertz band. So there are at least three things in this formula which do explicitly depend on time. The two in green, let me address first, because those are actually not an issue. The asteroid is obviously going to move on some sort of elliptical orbit. Ellipticities are like 0.3 to 0.4, at Eros is 0.25. So this thing has some fairly large variation in its distance from the sun over its orbital period. But the precise point is that is at the orbital period. So this is at between 10 to the minus 8 and 10 to the minus 7 hertz. And that actually falls off exponentially quickly, moving to higher frequencies. So that would not give you noise in our band. On the other hand, the other thing that depends on time here is the effective area that the asteroid presents to the sun. So this is a combination of geometrical area effects and also surface reflectivity effects. And that thing's going to be strongly modulated, but it's going to be typically strongly modulated at the rotational frequency and higher frequencies. It's not going to put noise into lower frequencies lower than the rotational frequency. So those two things are going to give you noise at both below our band and above our band, but not in our band. The thing that is actually going to give you noise in the band, though, is the actual direct fluctuation of the solar output, which actually does fluctuate on these relevant timescales. So the estimate I'm going to show you here is basically how much the solar output fluctuates and causes this acceleration to fluctuate as a function of time. So you can basically take this estimate and turn it into an estimate for the acceleration amplitude spectral density at the relevant frequency by utilizing the measured value of the solar power output, or the fractional solar power output fluctuations on relevant timescales. This has been measured because it's of interest for various other things as well. And you can convert that to a characteristic strain sensitivity, assuming for the purposes of this estimate that we have a fixed 1 AU baseline between two sort of similar types of asteroids. Once again, that baseline will vary as your asteroids move around the solar system because you're not formation flying asteroids. in any way. But again, that's going to give you noise which is below our frequency band for a similar reason that as I mentioned earlier with the variation of the asteroid distance to the sun. So I can basically neglect that effect for the purposes of this estimate. So before I show you some estimates, let me just briefly orient ourselves as to the parameter space I'm talking about. So here is characteristic strain as a function of frequency. This is 10 orders of magnitude on the vertical scale, 5 orders of magnitude on the horizontal scale. Here's LISA with its excellent strain sensitivity between 1 microhertz and 10 microhertz. Shown here in a sort of light dashed purple is the mu Juarez, a conceptual Strawman mission proposal, just for comparative purposes. What I've also shown here is various astrometric sensitivity estimates. This is other work people have done trying to estimate how well you get into this band. And you can see you can have access to this band, but at relatively modest levels of strain sensitivity compared to what mu Juarez was proposing, for instance. And then just for comparative purposes, I've shown one pulsar timing array limit here. These are the 11-year limits from Nanograv. I just happened to choose those because I had the data available very straightforwardly. I could have also put on EPTA, PPTA on here as well. They give limits which are in the same ballpark, maybe slightly better than Nanograv limits. But this gives you an idea of where PTAs lie on this curve. So now let me show you what the solar intensity fluctuations look like on this parameter space. And those are basically these brown and red lines. So the different lines correspond to different estimates of the solar output taken at different points during the solar cycle. And you can see this already is quite encouraging that this is, down at levels of strain sensitivity, which are comparable to things that mu Juarez was proposing. So now let me step through a couple of the other estimates, which are sort of patterned in a very similar way. So the other thing, which obviously comes from the sun, is the solar wind. The solar wind is also fluctuating in the relevant frequency band. And so we can make an estimate of how much the solar wind is going to kick the asteroid around. And that's shown here by this green band. The solar wind is monitored in real time by the CLAS MTOF proton monitor on the SOHO satellite. And so this has got less of a DC acceleration on the asteroid than the solar intensity, but it has larger in-band fluctuations. You can see this sort of has a stronger noise source between, say, millihertz and microhertz and 10 microhertz. And so those are sort of the direct solar fluctuations impinging on the asteroid and moving its center of mass around. The other thing you might want to worry about from the sun, and by the way, we've also checked that the torquing from this is not a problem. That's actually typically at a slightly lower value than the center of mass fluctuation. So the other thing which you might worry about is the fact that the asteroid is undergoing thermal cycling as it rotates on its 4 or 5 hour period, and the sun's heating up and cooling down the surface. That's of course going to give you a gigantic amount of noise right at the rotational band, and I'll show you where those lie on the slide on this plot on the next slide. But the other thing which comes out of this is that because the solar intensity fluctuates on longer timescales, it's going to change the equilibrium temperature that the asteroid reaches on those relevant timescales. And so that's going to cause the surface of the asteroid to expand and contract by a small extra amount compared to this large, motion at its rotational period. And that's going to be a noise which is in band because we know the solar intensity fluctuates at the relevant timescales. And so this gives you a noise estimate shown by these pink curves, which limits your higher frequency sensitivity here. Of course, as I've already said, you get cut off quite severely by noise at the rotational period, both because the asteroid itself is executing very large rotation. Your probe on the surface of the asteroid is moving around by kilometers at the rotational period. So there's of course going to be strong noise associated with that motion. And also, modulation of other noises at the rotational period will be quite severe. So what I'm showing you here is just bands associated with the 4 or 5 hour rotational period, and then it's harmonics. So this is going to cut you off somewhere around 10 to the -4 hertz going to the high frequency side. You may wonder why I cut this plot off at 10 to the -7 hertz. Why didn't I keep going? Because this looks naively like, oh, you're going to be able to do much better than PTAs, but that's not the case. Actually, what cuts you off is a effect we discussed in a paper last year, which is basically that for any inner solar system baseline gravitational wave detector of the sort of ranging type, you're going to get cut off at low frequencies by the fact that there are like 10 to the 6 other asteroids in the solar system. And those are moving around relative to your test masses, putting gravitational pulls on the test masses. And there's so many of these objects that they give you a background which can't be fitted out in a sufficiently good way in order to claim any sort of signal detection in that frequency band. So this cuts you off quite severely below, say, a few times 10 to the -7 hertz, and that cuts off our acceleration, our characteristic strength sensitivity at low frequencies here. So this looks, but this is basically all the dominant noise sources which we are able to identify, and this looks very promising, right? This is a lot of parameter space here, which appears to be between PTAs and LISA, which this would potentially make accessible to you. Just a word or two about seismic noise. So, of course, seismic noise on the Earth is a big problem for gravitational wave detection. We think that this is going to be much less of a problem on asteroids because the asteroids don't have tectonic plate motion. They don't have a molten core. These are just old dead pieces of rock floating around in space. And if you pick asteroids that are sufficiently solid, there shouldn't be an issue. In particular, you can estimate that what the resonant frequencies are for like perturbing an asteroid, something like 433 Eros. This has been done in the literature already. And the lowest sort of normal mode frequencies, if you were to whack the asteroid, are going to ring at something like 10 millihertz, which is way above our band.
You have 5 minutes left.
Great, thank you. Moreover, although no one has yet made in situ measurements of seismic motion on an asteroid itself, measurements have been made on both the Moon and Mars of typical seismic activity on those bodies, which are much more dead than the Earth in terms of their seismic activity. And you actually find there that amplitudes of typical seismic motions on those bodies are around a few nanometers around the Hertz, sort of around Hertz, which would correspond to something like a strain of 10 to minus 20 across AU baselines. So that would be easily good enough for our purposes, provided that was sort of the typical seismic motion in our frequency band as well. But that said, no one has yet done in situ seismic or plastic deformation measurements of asteroid surfaces as a function of time. So we think this is a very well-motivated thing that should be done as sort of a developmental goal to turn the sort of mission concept into a more full-fledged proposal as we move down the line. And this is also, by the way, already strongly motivated by what you might term planetary defense considerations. If an asteroid is about to send us the way of the dinosaurs, you might want to knock it out of its way, but that also depends on knowing something about the internal structure of asteroids to know how effective that's going to be. And that's already been something which people have thought about doing. So we would strongly encourage further seismic or actually in situ seismic measurements on asteroids themselves in future. So just a couple of words about the link itself. Our main point on this paper is to demonstrate that asteroids are sufficiently good test masses, and I hope I've convinced you that that is the case. We also, however, have to complete the gravitational wave detector by forming a link between the two asteroids. So two things I just want to mention here briefly. The first is clock noise. If you're doing some sort of ranging measurement across the baseline, you need good atomic clocks on both ends of the baseline. So your base station is going to have to include some sort of space-qualified atomic clock. We've been able to estimate that using the current best ground-based atomic clocks, you'd be able to access this band at interesting levels of strain sensitivity. Now, of course, there's a significant technical barrier from going from ground-based atomic clocks to putting them in space. So we would strongly encourage future research on that as well, although that's also very well motivated already, particularly from considerations about some of the mid-band detectors, and putting atomic clocks in space is something which there's a lot of significant interest in at the moment. And so those sorts of developments will aid this proposal taken going forward. And we also know that clock improvements have sort of been on an exponential trajectory for the last few years. So we don't think that clock noise in particular is going to be a challenge here, although there will be a lot of work that needs to be done in order to space qualify atomic clocks of the appropriate sensitivity. And then finally, just to say some words about the actual noise in the link itself. So of course, if you're doing some sort of ranging measurement between asteroids, you need to worry about shot noise in the baseline if you're doing it with lasers, or sort of thermal noise if you're doing it with radio. Using relatively modest proposals for how you'd be able to do that, relatively modest parameters about the systems that we'd be able to put in place to do that, we were able to again access this band at relatively good levels of strain sensitivity. And just to note here that this is a significantly less technically complicated optical system than, for instance, that which is flown by LISA. We're not going to get anywhere near the LISA band with this proposal, and because we're at much lower frequencies, we can significantly relax the technical requirements of the optical system in order to do this. And you'll notice here at high frequencies, I mean, we're orders of magnitude above where LISA is able to obtain sensitivity because of the fact that we're using a significantly relaxed optical system compared to them. And in fact, doing exactly LISA-style heterodyne interferometry between uncontrolled asteroids that have relative motions of kilometers per second would be quite tricky. So just to sum up then, let me show you just sort of one combination plot, which is basically a smooth version of all the noises I've already shown you. So this is sort of smoothed and enveloped curve here. This is showing a sensitivity projection for this mission concept using asteroids as test masses. I think you can see that there's a significant amount of potential reach here between PTAs and LISA. So of course, we're going to be sensitive below the LISA band and above the PTA band. There's a lot of parameter space here, which we think we can potentially access. And you can do this straightforwardly, somewhat glibly, by just landing base stations on asteroids and ranging between them. It doesn't require you to do the test mass engineering. It just requires you to do the engineering of the link to get onto the asteroids. Of course, there's two particular developmental things that I've pointed out here, which we think are subject of future research, which should be done, is in situ measurements of seismics on asteroids in order to just quantify exactly how bad that the seismic noise might be. We don't think it's going to be a problem, but it would be good to have in situ measurements on future asteroid missions. And the other thing which is going to be required here is, of course, the space qualification of atomic clocks. We think this is further motivation for that line of research. So with that, thank you for your attention, and I'm happy to take any questions.
Okay, thank you very much. You're exactly on time. Do we have questions, comments? We did have a comment from Alex Jenkins advertising his work with Diego Blas on constraining a similar region of the parameter space. We've got a question from Ranjan. Please go ahead and unmute yourself.
Hi, Mike. Thanks for the very nice talk. I have a question. I mean, so these asteroids are, I mean, the atomic clocks that you hope to land on the asteroids, they're also subject to cosmic ray bombardments, right? So you talked about the solar wind, but what about higher energy cosmic rays? I mean, how will you keep your atomic clock stable with respect to those things? I mean, their fluxes are slightly lower.
Sure. I mean, I think this I think is sort of part of the engineering challenge of space qualifying the atomic clock. So I mean, I'm not a clock expert, so I don't think I'm particularly technically qualified to make any sort of intelligent comment on that particular point. But this would of course be part of the technical challenge associated with space qualifying atomic clocks, and I think that's why that line of research would be something which we would, definitely be very, very happy to see done in coming years.
Can I ask one more question?
Sure.
Yeah. So what happens when comets perturb the asteroid belt? Like there are lots of comets on the inner solar circle, right? So they perturb the asteroid belt quite a lot.
Yeah. So this is actually, I mean, particularly if you think about actually, I mean, asteroids themselves are a strong perturbation here, right? So this asteroid gravity gradient noise estimate we actually did last year. We actually did some modeling of how much gravitational perturbation you get from other objects moving past you, and that's what this estimate actually is. And in particular, this takes into account some of these close passes as well. So this blue band here is an estimate for close passes. We've also checked, for instance, direct collisions don't seem to be a problem. If you're thinking about just sort of transient passage of something like a comet very close to the inner solar system, that's also something potentially which you'd have to think about. But I mean, provided that you have a sufficiently large comet that is a problem, you could also potentially veto out the period of time where that particular comet is going through the solar system. But using the combination of all the asteroids in the solar system that we were able to simulate, which is much, much more mass than individual comets going through the solar system, that's why this noise comes out as this blue line here. So I don't think individual comet passages per se would necessarily be a particular concern here.
All right. Thank you very much.
Thanks.
Subodh, please go ahead.
Hi. I was wondering about the difference between precisely the nature of ranging. So you mentioned that laser ranging and radio ranging are possibilities. I'm just imagining if you have asteroids that are sort of rotating around and lasers are very directional. I wouldn't even be able to imagine how that would work. And in particular, I'm imagining. So please correct me if I'm wrong. That really radio ranging is probably the most feasible thing to use. And then, if so, how accurately does it compare? Can you actually get to very small strain sensitivities with radio ranging compared to laser ranging? So if you could just elaborate on that, I'd be really grateful.
Sure. So I mean, yeah, I think this is part of the sort of the technical challenge of doing these ranging links is that you would have to somehow point the lasers at each other as your asteroids are rotating around and also orbiting around the solar system. So there would be some, engineering challenges associated with getting that to work. You would need sort of telescopes which you could actually point at to make sure the asteroids are actually, you're pointing the lasers at each other as you move around. The other potential way of doing this is something like you put a bunch of retroreflectors on the asteroid surface, and you put a spacecraft in orbit around the asteroid, so you know where your spacecraft is compared to the asteroid, and then the spacecraft itself is stable, so you can then do the shoot the laser from the spacecraft, but then you know exactly where the spacecraft is compared to your test masses. That's one proposal we sort of kicked around a little bit. But yeah, I mean, sure, you definitely do need to put some sort of systems in place that would keep the lasers pointing at each other if you do this with laser interferometry. The radio thing, I mean, here's just the estimate shown in sort of teal here of what we thought for a straw man radio type proposal. This was something like 150 watts of power using a relatively large radio dish. This is like a 4-meter radio dish, although you don't have to engineer radio dishes particularly accurately in order to do this. At something like 100 gigahertz, assuming something about the Q factor and noise. So this is maybe a little bit of an aggressive proposal for doing radio interferometry, but you could relax some of these requirements somewhat, and you'd be able to still access this band at sort of interesting levels of sensitivity. And I think you're correct in saying that the technical pointing requirements associated with doing radio might be somewhat simpler, because you could do, it wouldn't require you to do pointing as well as with lasers.
Thanks.
John, would you like to ask your question?
Okay, thanks. So very nice talk. I just wanted to respond a little bit to Ranjan's question about the atomic clocks in space.
Sure.
I just have to say there's a lot of interest in deploying atomic clocks in space for all sorts of things, like absolute timing. It's also maybe a stepping stone towards cold atom interferometry experiments in space.
Yep.
And so I think that we've succeeded in persuading the European Space Agency to prioritize R&D studies on this. I'm sure that NASA is thinking along the same lines. So I wouldn't worry about that too much. I think that's going to happen.
Okay,
Yeah, thanks. Yeah, that's actually a very exciting development. I'm very happy about that. So that'll be great if that can be gotten done.
Okay, I don't see any more questions or comments. Thanks for sharing that, John, and thanks to all the speakers for their wonderful talks. We're somewhat over time. Apologies to the organizers. This is the difficulty of remote conferencing, I suppose.
No problem at all. I think we should have a 5-minute break and then resume. So, well, yeah, let's resume, let's say 17 past 4. Thanks to everyone and see you in a moment.